Three-phase induction regulators. And the working principle of these induction regulators are similar to that of induction motors. So first, induction regulators. Induction regulator will be working as a constant voltage transformer. It will be working as a constant voltage transformer. One winding which can be removed, can be moved with respect to other secondary winding and obtain a variable secondary voltage. The primary winding is connected across the supply line. And secondary winding is connected in series with the line. When the position of one of the winding is changed with respect to other, the secondary voltage injected into the line is also changed. So when load on supply system change, voltage also change. To control this voltage, we require a induction voltage regulator. The working of induction voltage regulator is similar to that of induction motor. The construction difference or construction of these windings are: first we are discussing for single phase, and then it will be combination is applicable in three phase. So first we will be discussing in detail how the induction regulators are constructed for single phase. So the single phase induction regulator consists of stator and rotor. So in the case of stator will be working as primary winding of transformer, and rotor will be working as secondary winding of the transformer. The secondary winding is connected in series with the line where we want to control the voltage, and rotor does not allow to rotate continuously. This is the major term. It is not, rotor is not rotating, so then it is not rotor. The rotor does not allow to rotate continuously. A rotor is not continuously rotating, and only the position is adjusted. When the position of the secondary winding is changed with respect to the primary winding, the injected voltage in the line also change. So first, how this will be constructed or how this will be working. We have this induction motor. And we have rotor. We have these windings. We have rotor winding, and similarly we have stator windings. In machine, you have studied that dot means dot and cross. That indicates incoming and outgoing. So we have V1, which is connected across and then we have this V2, which we get and this is also connected to this. So this will be your this is your rotor and this is your stator. This will be working as primary winding and rotor will be working as secondary winding. So its equivalent diagram, we can easily find out that it will become, this is your V1, we have this A and this is B. So this will be your primary windings and then we have secondary windings, which this common point C is connected to A and then we have this B point and we will be getting this voltage V2. So it will be deciding on the basis of what is this small v, and on the basis of this it will become V1 plus minus small v. This will be your I1 and this will be your I2 and we have this current IP. So this is how the basically the single phase induction regulator will be constructed. So when the supply voltage is given to the primary winding, an alternating flux is produced in the primary winding which cuts the rotor windings. The induced EMF in the rotor winding is due to the interaction of rotating flux and the secondary winding, that means rotor winding. The magnitude of the rotor EMF depends upon the position of the rotor with respect to the stator. So this is the simple induction motor principle which this is using. We have supply voltage to stator windings. That means primary winding of the transformer, equivalent primary windings. It will produce a alternating flux phi m, and this will cut the induction motor rotor. That means secondary winding. And this induced EMF in the rotor winding voltage is induced in the rotor winding due to rotating flux and stationary rotor. So when these two interacts, there will be a voltage is induced in the rotor windings, and the magnitude of rotor EMF depends on position of the rotor. So this is the basic working of this regulator, induction regulator. The basic difference between induction motor and induction regulator is, in induction motor, the rotor is continuously rotating. This is continuously allowed to rotate in the induction motor. But when we are working in using it in the form of induction regulators, it is not allowed to move continuously. Only the position of this rotor is changed with respect to stator for getting the different condition of the system. So let's consider a simple So initially the rotor position is 0 degree with respect to the stator winding. So the flux which is cut by this rotor winding is almost 0. So this is the initial position. So we don't have any voltage regulation in this case. This will be point A, this will be B. Then we will be having this C and this as D. Sorry, this will be your C and this will be your D. So it will be like this. We have this flux phi m, and we have also have this rotor position. This will be your 0 degree. So now the second will be this stator will be the same, only we will change the rotor position to 90 degree. This will be your D and this will be your C. So it will be 90 degree in the case of second. Then similarly we will be having 180 degree, and similarly we will be having minus 90 degree. So how now this will be working? So when first case is your boost voltage, second is your zero voltage. Third is your buck voltage. So boost voltage when rotor is at angle 90 degree in clockwise direction. The rate of change of flux linkage in the rotor is maximum. Therefore, it produced maximum EMF in this direction. It is known as the boost condition because it will be increasing the voltage, because we have this V1 and then we have same small v in the same direction. So we have V2 as the resultant voltage, which is more than the supplied voltage. So when V1 reduce, this induction regulator will be set to a 90 degree clockwise direction with respect to the stator, and its voltage, output voltage, that means the receiving end voltage and sending end voltage, will become more than the V1 is your receiving end voltage and V2 is your sending end voltage. No, V1 is your sending end voltage and V2 is your receiving end voltage. So voltage is increased in the case of when the rotor is at an angle 90 degree in clockwise direction. Then we have this zero voltage condition. That means rotor is at 180 degree. The rate of change of flux linkage with rotor will become zero. Therefore, there is no induced EMF in the secondary winding, and your primary voltage and secondary voltage will become same. That means V1 and V2 are same when the rotor is at 180 degree and also at 0 degree. When the rotor is at 270 degree in clockwise direction or 90 degree in anti-clockwise, that means minus 90 degree, the rate of change of flux linkage is maximum, but it is in opposite direction. Therefore, the secondary induced EMF is in opposite direction to that of primary voltage. So in this case, we have this V1, we have the small v in the opposite direction. So we getting V2 as the less than the V1. Primary voltage will be more and secondary voltage will be less. So this will be working in buck voltage direction. So this is how this, and the magnitude of the induced EMF depends upon the sign of the angle between the two windings. That means induced voltage is directly proportional to sign of angle. So this is how the single phase induction regulator is working. And the rating of the induction regulator is the product of its full load current, voltage boost, and number of phases. The advantages which are associated with this is Advantage of this system is it provides constant voltage at the load side under varying load conditions. It's find widespread application in the high voltage circuits. And disadvantage are high cost, noise due to vibrations, and proper design is required to avoid waveform distortion. So the single phase induction regulator is almost similar to that of single phase induction motor, except that the rotor is not allowed to rotate continuously, but can be adjusted in any position manually or with the help of small motor. The primary winding is wound on the stator and is connected across the supply line. The secondary winding is wound on the rotor and is connected in series with the line whose voltage is to be controlled. The primary exciting current produces an alternating flux that induces an alternating voltage in the secondary winding. The magnitude of the voltage induced in the secondary windings depend upon its position with respect to the stator, that means primary winding. By adjusting the rotor to the suitable position, the secondary voltage can be varied for a maximum position to the maximum positive to the maximum negative value. In this way, the regulator can add or subtract from the circuit voltage according to the relative position of the two windings. Due to this greater flexibility, single phase regulators are frequently used for voltage control of distribution primary feeders. So this is how basically the single phase induction regulators are working. Now, when we are talking about three phase induction regulators, the three phase induction motors have three primary and three secondary windings. So when we are talking about three phase induction regulators, we have three primary and three secondary windings, which are 120-degree apart. That is similar to the three-phase induction motor. The primary windings are placed in the slot of the laminated rotor core and connected across the three-phase supply. The secondary windings are in the slots of laminated stator core and are connected in the series with the load. So the three-phase induction regulator equivalent diagram will be so these are your primary windings, P1, P2, and P3. And then we have this secondary windings. These are your S3, S2 and S1. So when we are talking about single phase, three phase, it is three windings only which are connected in star, and the regulator does not require any primary and compensating windings because the secondary winding of the regulator is magnetically coupled to one or more primary windings of the regulator. The rotating magnetic field of constant magnitude is produced, due to which the voltage induced in the secondary is of constant magnitude. The phase of the regulator varies with the change in the position of the stator. So when we change the position of the stators, we will be changing the positions of the interaction of the flux with the stators, and we will be getting the voltage according to this. So when we are talking for one phase, we have this V1, and then we have this small v, which depends on the angle. This is theta, and on the basis of this we will be getting V2. So this will be like a circle. This is your V2 max, and this is your V2 minimum. So V2 max when we have 90-degree angle, and V2 minimum when we have 270-degree angle. So on the basis of this, we will be getting, this is your angle delta. The phasor diagram of the induction regulator is this, where V1 is the supply voltage, small v is the induced voltage in the secondary winding, and V2 is the output voltage per phase. The output voltage is obtained as the phasor sum of the supply voltage and the induced voltage for any rotor displacement angle theta. The locus of the circle is continuously circle drawn with a center on the edge of the supply voltage and of radius small v. The maximum output voltage is obtained when the induced voltage is phase with the supply voltage, and minimum output voltage is obtained when the induced voltage in phase with the opposition with the supply voltage. So in construction, a three-phase induction regulator is similar to that of three-phase induction motor with wound rotor, except that the rotor is not allowed to rotate continuously but can be held in any position by means of the manual or motor. The primary windings either in a star or delta are wound on the stator and are connected across the supply. Primary winding, stator, connected across supply. And the secondary winding are wound on the rotor and the 6 terminal are brought out. Since these windings are to be connected in series with the line whose voltage is to be controlled. When polyphase current flow through the primary winding, a rotating field is set up which induced an EMF in each phase of rotor winding. As the rotor is turned, the magnitude of the rotating flux is not changed, hence the rotor EMF per phase remain constant. However, the variation of the position of the rotor will affect the phase of the rotor EMF. The applied voltage is shown in the figure. The input primary voltage per phase is V1. The boost induced by the regulator is small v, and the output voltage is V2. And V2 is the vector sum of V1 and small v. Three-phase induction regulators are used to regulate the voltage of feeders and in connection with the high voltage transformers. So this is how the three-phase and single-phase induction voltage regulators are working. If anyone have any